the action scene right off the bat, no context, and then after that they take a break and they go back and do a couple of flashbacks. This is that, but in a math context, I guess. So, and not quite probably as entertaining, but maybe we'll see. So this is the geometric representation of completing the square. So I'm going to take you through these problems real quick. Not real quick, but like without delay. And then I'm going to give you some time to work on an activity, a Desmos activity. All right, so which is a little bit more user friendly. The idea here is for you to get an idea of where this term completing the square ties, or how it ties with the geometric thought process of completing a physical square. Right? Because we talked about completing the square as it is completing a perfect square trinomial, but it also has a geometric manifestation, right? Which is kind of cool. And it ties together a little bit, well, a lot of it, with what we were doing in the last unit when, actually 2 units ago, when we were multiplying binomials and drawing the rectangle to come up with the geometric manifestation of that. Right? So that's what this is getting at. All right. So we have x squared plus 4x plus c. This is the reason why we skipped all those problems earlier on those subsequent pages, because we wouldn't have known how to do them yet. All right. So the idea is that anytime you see a problem like that, I would be looking for you to draw a picture. All right. So what we have when we have x squared plus 4x plus c is the need to determine that perfect c value to make this a perfect square trinomial. All right. So it's almost like, so this is the same as x squared plus 4x plus blank. All right. When we would complete the square, we would leave a little space to complete the square. The c is a placeholder for that space. All right. And we already know how we could figure that out. We can take the b value, cut it in half, and square it, and we'll get our answer. But we want to see how that would work geometrically. All right. So what we do is we determine, based off of the number of x squares, how many big squares we have to have within the dotted or dashed larger square. All right. So we have one of those squares. So I'm going to have 1 x by x square giving us 1x squared. All right. Then we have 4 x's. All right. So 4 of those x's. Now we know opposite sides of a rectangle are congruent. So this side is going to have the same length as this side and this side. So if I tell you that this side has a length of 1, then we have a square of a rectangle that has an area of just 1x. All right, so I have 1x squared and 1x. Now I need 4 x's, not 1x. So I need 4 x's. So I would need 3 more of those 1x's. Well, I could put one here. All right, I'm going to resize that a little bit. Okay, I could put one there. All right, that looks like it's about the same size. All right, and it ought to be. I can take this distance here, this one, and apply it down here, making another rectangle. With dimensions 1 by x, giving me another 1x. Then I would just need one more of those. Gonna just kind of tweak it a little bit, give it a little bit of a better fit.
Could you also put it to the right of the first one?
Like on this side here?
Yeah.
You technically could, but we want it to kind of fit together with the approach that we used 2 units ago. That was a while ago. But that's how we placed it then. Just for consistency, this is where we would put it. But if you put both of these rectangles over here, it would still technically be correct. All right. So what we're looking to do here, so now I have 4 x's in total. I have 1x squared and I have 4 x's. Now I'm looking to figure out what it would take to complete the square. All right. There's an entire square that could be made out of this. I need to know how I can complete that. So in order to do that, I would need to know what this value would be in terms of area. Now, we can't necessarily make the assumption that it's just another x squared because we don't really know that. Just because it looks like it's the same size doesn't mean it really is. But what I do know is that this piece here, oh, that jumped on me, going from here to roughly here, has a length of 1, all right, just kind of following down this line extended. This one also has a length of 1, again, because opposite sides of a rectangle are congruent. If I extend this line, this one would have a length of 1, and so would this one. All right, so each one of these squares are 1 by 1. So 1, 1, 1, 1, that gives us a result of 4. All right, each one of these would amount to an area of 1. Since there's 4 of them, 1 plus 1 plus 1 plus 1, or 1 times 4 would give you a 4. And so that's what it would take to complete the square. So that must be what the C value is. All right, and that's the geometric representation. Now these are fairly straightforward numbers. They're not terrible, but you know, it's still a little bit of work. And this one had the first first square and first rectangle given to you, so you know we would have to take care of that too. But yeah, anyway, I'll do a couple more. But this would lead us to the expression on the bottom, x squared plus 4x plus 4, which we then know is a perfect square trinomial, which would factor to x plus 2 times x plus 2. And it's like, well, how do you know that? I'll get to that in a second. X plus 2 times x plus 2 is the same as x plus 2 squared, which was the whole point of doing this, right? So back to the whole how we know it's x plus 2 times x plus 2. Aside from using a factoring skill, you know, just factoring the x squared plus 4x plus 4, the dimensions of the overall square, the largest square here, let me get a different color. That's not really popping out the way I want it to. Get this one. This side here and this side here, the area of the whole thing should be the same no matter how I represent it, whether I add up the individual components or if I do length times width of the whole thing. Well, this whole side here has a length of x plus 2. Same deal on the top. It's a square. Oh, that got covered. Same deal on the top, bottom, and right side. So 2 dimensions are x plus 2. So that would mean that the 2 factors are x plus 2, leading us to x plus 2 squared. All right, so geometrically we get the same result that we would get if we were to do it using the algebraic approach. All right. So you get to the second one, x squared plus 6x plus c. Let me draw a big old square to get started. All right, I need to fill the rest of this space and this space with a total of 6x. All right, they're two equivalent areas. So that means I have to split that 6x. All right, so this whole piece here has to amount to 3x. And this piece has to amount to 3x. So I just got to figure out how that's going to play out. Well, if I know that the dimensions here are x by x, giving us x squared, the only way I'm going to get a 3x would be knowing that this side here has a length of x, would be if they're each x by 1. That would give me an x. I would need 3 of those in each region. All right. So I'm going to draw a skinnier rectangle. Hopefully not too skinny. Okay, totally too skinny. Pretend it fits. Oops. You know what? Let's not pretend. Let me do it right. No, that's going to be too big. I feel like right there is where I want it. All right, so each one of those is going to be 3x. Same deal here. All right, because again, dimensions x by 1. X, x, x. Again, x by 1, x, x, x. All right. So we know the length, you know, I can kind of do this a little out of order here too. The length of the entire side here, we now know is going to be x plus 3. All right, we would just need to figure out what it's going to take to complete the square. All right, so that would be what that c value is. What's it going to take to complete the square? If I break this up based off of these lengths, so a couple of consistent all the way through, we're going to end up with a total of 9 squares with area of 1, because we know that the dimensions are 1 by 1 in each case. All right, so that would make the c value 9, and the factors x plus 3 by x plus 3.
Could we write x plus 3 squared?
Yeah. All right, and so the only other variation here is what you would do if you already had a c value there. All right, and we would handle that the same way we kind of handled every other case, and that is sort of disregard that, work around it. If it were an equation, we would move it off to the other side, but at least for now, we're just going to pretend it's not there. So ignore the 3, complete the square, and then see what it's going to take to make that 3 into that new number. All right, so we're just going to focus on this information here. I need an x squared and an 8x. So I'm going to draw a big old square. Fit it in. I need to break this up into quarters, so that should be a little easier, at least sizing wise. Okay, right on cue, I screwed that up. Defend. All right, that's close enough. So I get an x squared. I have 4 x's across the top, 4 x's going down the side, because it's x by x by 1. We know, and it's vertically also, that this whole thing has to be x plus 4. I don't think I have enough room to get it in there. Tuck it in. That's x plus 4, that whole side. All right, but we can hold on to that. It's really just a matter of determining how many squares of size 1 we would have in this region here. I'm going to do it without the dotted lines here. So it's going to take a total of 16 to fill in that space. All right, so the ideal number would be 16. Oops. We already have a 3 there, though. So to complete the square here, we would need 13 more than we already have. All right. So to complete the square, we need 16 1-unit areas. We already have 3. All right. That plus 3 is 3 1-unit areas. We would need 13 more. All right. So if we're talking about actually completing the square, the 16 is the number that you would add to both sides of the equation, but this is the justification of that. This is where that all comes from. All right, so it's a little bit of an origin story, but I don't think it has as much context until you've already experienced completing the square a little bit.
On an assessment, will we be doing something like this, or is this just for our own understanding?
Yeah, you're gonna have to do it on a test, yeah. X that needs to be split among the 2 regions. So 5 x's on the top right. So I'll need 5 x's on the lower left. So I'll do a quick copy paste job. We know we already have the 17 1-unit squares. We kind of just keep that in mind. All right. So dimension wise, we'll have an x over here, and then we'll have 1, 2, 3, 4, 5 more units. So that means that this whole side here has a length of 5. We'll have an x and 1, 2, 3, 4, 5 units, which means this whole side has a length of 5. Now you could, I mean, 25 is not terrible. You could populate this with 25 1-unit squares. I'll just do it in this one instance because it's, like I said, it's not crazy. But if there were like 100, 10 by 10, that would be a different story. All right. Even this is borderline what I'm willing to do. right? So to complete the square, we would need 25 1-unit squares. But we already have 17 1-unit squares. So we already have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I mean, you wouldn't really need to shade the diagram to figure out that you need 8 more, because if you have 17 and you need 25, you need 8 more. But this is a good visual representation. So we would need 8 more 1-unit squares to complete the square. All right. So that's another kind of twist on the whole idea. All right. But it's kind of strange because if you really think about it, we have been doing that all along. It's just we've been doing it in the form of an equation. All right? Because we were moving that 17 out of the picture by subtracting it to the other side of the equation, then completing the square, and then manipulating it from there. All right? By moving that 17 out of the picture and completing the square, we're essentially using this process. All right?